that the section doesn't experience local buckling. The web and the flange doesn't experience local buckling, okay? So the way we do this is we use the guidance from Eurocode 3. So in Eurocode 3, there are two tables that we have to follow. We have to check both the web and the flange. So that's why there are two tables, one for web, one for flange. Okay, so you need to check both. All right. And so what the table basically does is it checks the length of that member divided by the thickness. The ratio, basically it checks for the ratio. The length divided by the thickness generally. Okay. So that this table gives you limitations on the length versus thickness ratios. All right. Now, to get the actual dimensions of the beams, so as I mentioned yesterday, right? So for steel sections, you cannot simply specify your own depth. You cannot simply specify your own width. Steel sections, you can't do it because everything is prefabricated in a factory. So there's a catalog of sizes already. So you choose from that catalog of sizes. You cannot come up with your own size. All right. So to get that catalog of size, there's a source where to get it, but I shared with you. Okay. I shared the one for UB, Universal Beam, for you. Okay. It's the Excel file that I shared yesterday, and I'll teach you how to use it. So I think I got it open as well. I need to stop sharing. Let me share that table. Let me share that table. There. You see my Excel? Can you see the Excel? Can you use your mic to reply me? Don't use text because I'm not looking at the Google screen. Google Meet punya screen.
Can, Doctor.
Can? Okay, thank you. All right. Okay, so this is the table, or rather the catalog of all the sizes that you can choose from. Okay, this table is only for UB section. UB section. There are other tables for UC, for the rectangular hollow. Okay, but we are not going to worry about that. The way you use it is the same. Okay, the way you use those are the same. For this course, we are only going to focus on UB saja. Okay, to make life simple. All right, but to use the other tables, it's the same process. Okay, right now. So this is the table. All right, showing all the steel sizes, the UB sizes that you can choose from. It starts from the heaviest or the biggest to the smallest. Okay. So if you look on the first column, the first column gives you the section designation, the size. So we start from, so basically this table starts from the biggest one. 1016 times 305. That's the first column. Okay. So the first column gives you the height of the section times the width of the section. So 1016 is the approximate height of the section. It's not accurate. It's not exactly. It's within the range of 1016. Okay. So 1016 is the approximate height of the section times 305, which is the approximate width of the section. Okay. And then in the second column times 584. That one is the weight. It's the weight of the section. So 584 here refers to 584 kilograms per meter length. So for every 1 meter, this beam, it's actually 584 kilograms. So more than half a ton. Yeah. So 1 meter length of this beam is more than half a ton. So imagine this is the biggest UB. Okay. It weighs more than half a ton. for one meter. So if you have 2 meter, you're already looking at 1.2 tons already, more than 1.2 tons already. Okay, so this is the way you read the table. The height times the width times the weight of the section per meter run. Okay, now as I mentioned, the weight, as I mentioned, the height and the width is approximate. It's not exactly 1016. Okay, to get the exact height and to get the exact width, you need to look at the column E and F. Column E and F gives you the exact measurement of the width of the height or the depth. It means the same thing. The height and the depth means the same thing. Okay. So the actual height of the section is actually 1056. You can see in column E. Yeah, 1056. Can I can I annotate that? Dapat pula. How do I annotate? Cannot annotate. Never mind. Let me zoom in. There, 1016, 1056. Okay. 1056 is the height. 314 is the actual measured width. Okay. And then the thickness of the web is 35 mm. The thickness of the flange is 64 mm. So basically, if I specify this section, 1016 times 305 times 584, basically what it means is I need to unshare this screen because I want to draw. Let me unshare. You keep it open. You keep your Excel open. I need to draw something. App. To share the app. Okay, all right, okay. Hope you can see my conteng screen. All right. If you can't, let me know. Right. So basically, what it means, okay. Basically, what it means is it's an I-beam. It's a UB. It's a UB. So it looks like this. Okay. So the height or the height or the depth, it doesn't matter. It means the same thing. Is 1056, guys. Yeah, 1056. Okay, 1056. The width is 314. All right. And then the thickness is 36 and 64. So the thickness of the web, TW, thickness of the web, berapa tadi? 36. The thickness of the web is 36 mm. The thickness of the flange is 64 mm. Okay. So this is for a 1016 times 1016 305 584. So this for 1016 305 Okay, so this for a 1016 times 305 UB 584 section. Okay, so this is how you call up the section. Okay, so this is the name, you can say the name
Reply to you, sir.
of the section.
Do you want to reply?
And these are the sizes of all the elements that make up the UB. Okay, there's one more. There's one more I forgot. There's a root radius. If I look back in my Excel, the next column, along column I, there's a root radius 30 millimeter. So what that means is actually this. So the root radius is. I deleted too much. Never mind. Let me redraw. My drawing not very accurate just now. Let me draw something more accurately. Yeah, like that. Okay. So the place where the flange and the wet meets, there's actually a radius. Let me zoom in. There's actually radius here. There's actually a radius here. That radius is 30 millimeter. Root radius. We call it R lah, root radius. So that radius, 30 mm. Okay. Radius. Okay. So there's a root radius of 30 millimeter for this section. Okay. Right. Okay. Any questions about the sizes?
For me, all clear.
Okay. Okay. Thanks, Sam. All right. Okay. Now that everyone's happy with the sizes, let's do the classification now. Okay. So let's do a classification. Using the Eurocode 3 table classification. All right. So for classification, let's do a 456 example. Okay. Classify a 456. 456 got what size? So if we go back to the Excel, later I'll show you the Excel. 456. 456. They don't have 456. It becomes 457. Last time it was 456. Okay, never mind. 457 191 82 lah. 457 192. Okay. They updated the table. Last time there's a 456. Now it's 457. 191 UB82. The rest are the same. Okay, so classify this section. 457 191 UB82. All right. So when you classify it, okay, you need all the dimensions, okay, to be able to classify it. So let's draw the big. And then don't forget the radius. There's a curve radius. And then another curve. Bottom flange. Okay. All right. I want you to use the Excel table for me. You open your Excel table. Tell me what is the height. Or they use D. I don't know what. Use D. Yeah. Even though they call it height, but no. They call it depth. But then they use the sign H. Height. basically means the same thing lah. Okay. So give me the height. Give me the
460.
width. Okay, height berapa?
460. Height 460.
Ngam.
Yeah.
Is there a point? Something? Tiada. Okay.
None.
Okay, none. Okay. The width?
191.3.
Okay. The TW?
9.9.
Okay. Okay, and then the TF?
16.0.
Okay, and finally the root radius?
10.2.
10.2. Okay, thank you. All right, okay, so you have all the dimensions. Okay, the next thing you need is you also need to know what steel grade you use. Okay, so yesterday in my introduction to steel design, I gave you 4 different steel grades. S235, S275, S355, and there's another one, S460, if not mistaken. Okay, so yesterday I mentioned to you there are 4 steel strength to use that you can choose from. Okay, these are the 4 different strengths, but this 235 not common. 235 only really you get in China. Okay, you only get in China. Okay, 460 also not very common. The common ones are 275 and 355. Okay, these are the 2 common ones lah. All right, so but normally in test exam, I will tell you what it is. I will tell you which one to use. Okay, so you just need to use the correct one. So normally in test, in exam, I will tell you, oh, okay, I want you to use S275. Okay, I'll tell you which one to use. Okay, and normally it's 275 lah. Normally you don't go for 355 unless you have a special case. Okay, so yeah, in test exam, I'll just tell you which one to use. So in this case, in this example, we will use steel grade 275. So that means the yield strength of the steel is 275 Newton per millimeter square. All right. So now let's do the classification. Okay. So to do the classification, easy. Okay. You don't worry about anything. Later, we will look at the table later. Okay. We are going to look at the table later on. Right now, you consider the wet. You do the web C over TW, and then we do the same for the flange. C over TF. Okay, now why do I call it, why do I say C? Why don't I just say H? Because it's actually not H. Okay, the measurement that you want to use is this. You cannot use the total height of the web. If you look at the table, maybe I'll open the table lah. Okay, no, okay. Let me explain it here. Then I switch to the table. Okay. Now for the web, the C is measured from the end of the radius. You remember there's a radius, there's a root radius, 10.2, top and bottom. Okay. There. That is the C for the web. Okay, so it's the clear distance, it's the actual distance of the web. Because when you're counting, when you're checking the web, you don't want to include the flange bar. Yeah, the flange is not part of the web. So you have to remove the flange from your calculation. And then you also want to remove the root radius from the calculation. So you concentrate purely on the height of the web. That's why they use C lah. Yeah. Okay. So that's the calculation that you want. Okay, now, and then for the flange, the C is, the flange is more simple. It's the total C, it's the total width. It's the total width of the flange, okay? Hey, no, it's not. Sorry, I don't think it is. I'm wrong. Last time it is. British standard, it is. Now Eurocode is not. It's actually, let me double check.
And
no.
a flange to root.
Correct. It's also measured from the root. Yeah. It's measured from the end of the root to the end of the flange. That one. C flange. Yeah. Okay. So remember, when you're checking the C for the web, it's, you have to remove the flange thickness, you have to remove the root radius, and you take purely the flange height. The web height. And then when you're checking the flange width, same thing. You want to remove everything else, remove the root radius, remove the web thickness. You just concentrate on half the flange only. Okay, so let me prove to you. If you don't, I prove to you later lah. You take my word for it. Later on, I'll show you. Okay, you take my word for it. Later on, I'll show you. Okay. Okay, so the way you do your calculation is, so C web. So this is actually, so the web is actually C web divided by T web. Okay, so what is C web? Calculate for me. 460 minus the flange thickness at the top minus the flange thickness at the bottom minus the root radius at the top minus the root radius at the bottom. How much? 460 minus flange thickness top and bottom. So flange thickness at the top is 16, bottom also 16, so 32, right? So 460 minus 32. And then minus the root radius. Root radius at the top is 10.2, root radius at the bottom also 10.2, so total is 20.4. So 407, agree?
Yes.
407.6. Yeah, 407.6. Divide by TW. TW is the thickness of the web, 9.9. Okay. So 407.6 divided by 9.9, 41.17. Okay. do it to 2 decimal places, to be accurate. 2 decimal places. Okay. 41.17. Okay. Flange, same. Flange is actually C flange divided by thickness of the flange. So C flange is the total flange width where you want half of it only. Okay, the easiest way is you take the total width first. One. Minus the root radius on the left and right, which is 10.2, 10.2, 20.4. Yeah, 20.4. So 161, but 161 is C flange for left and right. So you want to divide by 2, 80.5. Okay. And then the T flange is 16. So 80.5 divided by 16, 5.03. This is a ratio. So these are ratio. Therefore, no unitless. So these things are unitless. They are ratio. So they are unitless. Okay. So now we have looked for CTW, C divided by TW, and also C divided by TF. So we found the ratio. Next thing we want to do is we want to check what is the limit. Okay, so we already know the ratio. Okay, now to determine, okay, let me just write down. To determine if the section classification, so whether it's class 1 or 2 or 3 or 4, check the ratio against limit. Okay, so now we know the ratio. Ratio for the flange is 41.17. The ratio for the the ratio for the web is 41.17. The ratio for the flange is 5.03. We know the ratio, but we don't know the limit yet. Now we have to find the limit. Okay, to determine if the section is class 1 car or class 2 or class 3 or class 4, you have to check it against the limit. So the limit is this. You have to go back to the table. The limit is also on the table. Not the Excel table, not the Excel table. This table, the Eurocode table. All right. So there. So hopefully you can see my slides. Okay, so the first slide is for flange. Okay, so maybe let's do flange first. So you take a look just now. There. This is the section we're looking at just now. C for the flange, C is measured from end of the root radius to end of the flange, and then T is the thickness. Yeah, so you believe me? Okay, I just want to prove to you. And then for the web, also the same. There. It's between the root radius for the web as well. Okay, there. It shows you where the C is. Okay, so in test exam, I will give you this table. So you don't worry. You don't have to memorize this table, but you need to know how to use it. Okay, test and exam, this one will be given. Okay, these two tables. Okay, all right, now let's check the limit. Let's do flange first. Let's do the flange first. Okay, okay, flange. For flange, okay, now on the left hand side, the first column, you have, let me see if I can, how do I something? Okay, I can show. Okay, now on the left hand side, this is the class. These are the classes. You have class 1, class 2, class 3. Okay. Now, there's no class 4. Class 4, basically, if you don't meet the class 3 requirement, it's class 4 automatically. Okay. So basically, the way you check is like this. You check whether it's class 1 first or not. Okay. You check whether it meets class 1 or not. If it doesn't meet class 1, then you check class 2. If it doesn't meet class 2 also, then you go and check class 3. If it doesn't meet class 3, then automatically it becomes class 4. Okay, it's like that. Okay, that's how you check. You check one by one. Okay, you check with the best highest class. If it doesn't work, you slowly go down. Okay, that's how you check. All right. Okay. Next. So on the y-axis is the class. Y-axis. The vertical axis on the table is class. Now you also have the use a different color. Blue. Okay. Dark blue. Okay. On the x-axis, you also have the types of forces, because it depends on what type of forces you are subjecting your section to. Okay. Now, in our case, we normally check our section for bending. Okay. We normally check our section for bending. And when you check for buckling, you are only worried about compression. Okay. So imagine, go back to RC design. You have a beam. The beam goes into bending. The top is in compression. The bottom is in tension. Okay. So basically, the top flange is in pure compression. So what does that mean? That means, let me delete this. How do I delete? Now I can't delete this one, I think. Yeah. So imagine you have a beam simply supported. If I apply a load that way, the beam goes into bending like this. The top flange is in compression. The bottom flange is in tension. Okay. For section classification check, you are checking for buckling. Buckling only occurs in compression. Buckling only occurs in compression. Yesterday, I proven to you already. Yeah? Buckling only occurs in compression. Okay, so therefore, which table do you think we use? In the x-axis, kita ada 3. We have first row, second row, third row. We have 3 columns. We have column 1, pure compression. We have column 2, the flange partly in compression, partly in tension. We have table 3, partly in compression, partly in tension as well. The tip, it depends on what the tip is doing. Okay, which one do you think you use? If pure bending is this. You use the first row. Okay, because the flange will be in pure compression. The flange is in pure compression. Okay, so you just use that first table. Simple. Don't make it overly complicated. All right. Okay, so use the first column. Use the first column. All right. So first column, let's check one by one. Let's check class 1. So class 1. What is the limit? The limit is C over T has to be less than 9 epsilon. Remember this, huh? So to qualify as class 1, C over T has to be less than 9 epsilon. If it's more than 9 epsilon, then you go check class 2. Class 2 is less than or equals to 10 epsilon. Okay? So very simple. But the thing you have to calculate is epsilon. You have to find epsilon first. Epsilon is this formula. There's a formula for epsilon down here. Epsilon is square root 235 divided by your steel strength. Okay, and you actually have the answer there. What did I say our steel strength was? S what? Just now. What is our steel strength just now? S what? S275 or S355?
275.
Yeah, 275. So therefore, you look at the bottom. You look at the bottom row. Fy 275 epsilon is, yeah, for Fy of 275, the epsilon is 0.92. So straight away you have the answer, 0.92. So epsilon is 0.92. Okay. So let's check for class 1. For class 1, C over T has to be less than or equals to 9 epsilon. So let's check. So now I'm going to revert to my sketchpad. Yep. Okay. Okay. So now I revert back to my sketchpad. Make sure you can see it. If you cannot shout, let me know. All right. Okay. So let's check the limits. Limits. Okay. All right. So epsilon, let me just write it down. epsilon was 0.92 just now for S275. Okay. Okay. So the limit for the web is what just now? C over T W 9 has to be less than or equals to 9 epsilon, right? Oh, but that one for flange. Sorry, flange. It was for flange. Let me go here. Okay, flange, huh? Let me cut in half. So it's clear. Okay. Now we look at flange. For flange, the limit is less than or equals to 9 epsilon. Okay? So 9 times epsilon. Epsilon is 0.92 just now. So how much is 9 times 0.92? $8.28. Okay? 9 epsilon is 9 times 0.92, 8.28. Now, you go back and check. Our flange ratio is 5.03. Is it less than or more than the class 1 limit? Less or more?
Less.
Less, correct. Okay? So let's go back to our ratio. It's 5.03 just now. So this is less than 9 epsilon. Yeah? This is less than 9 epsilon. Therefore, okay, so this is class 1. It meets class 1 requirement. If it's more, then you go check for class 2. Okay? Now let's do the same for the web. For the web, you can look at the table yourself, but the limit is for the web 72. So for the web, 72 epsilon. Okay, so for the web, the limit is 72 epsilon for class 1. So let's check 72 epsilon. So 72 times 0.92. 72 times 0.92. 66.24. Okay? 66.24. Let's go back to our ratio. What is our ratio? 41.17. So 41 is definitely less than or equals to 66.24. Therefore, the web is also class 1. So therefore, the final answer, section is class 1. Because the web and flanges are class 1. Finish. Can you follow? Any questions?
Yes, Doctor. Can.
Okay. Do you want one more example?
Sorry, doctor.
Yeah.
I'm curious about the 72 times the epsilon. The
Okay.
72 is coming from what? Is it like fixed number for the web?
Yes. The
Ah.
72 is from this table. Let me, how do I unshare? Wait. What's my Google? Okay. If you have questions, make sure you ask. Okay. Right. Okay. So earlier, for the flange, we were looking at this, right? This table for the flange. You remember? This is for
Yes.
flange. Yeah.
Mm.
So let me remove everything so that it's clear. Okay. So for flange, you check 9 epsilon. If it doesn't work, then you go to class 2, 10 epsilon. If that doesn't work, then you go to class 3, 14 epsilon. But that's for flange. For webs, you go to the next table, next page. There.
Oh.
Webs,
Yeah.
yeah. So for webs, class 1 is 72 epsilon. Class 2 is 83 epsilon. Class 3 is 124 epsilon.
Okay. Okay.
Yeah.
Clear,
So
doctor.
that's where
Thank
I
you.
got the 72 from. Yeah.
Okay. Okay.
Okay. Okay. What about other people? Any questions? Make sure you ask. If you don't know, please ask. This is where you get free marks. This is the simplest calculation that you can do. Make sure you get marks for this. The other calculations won't be this simple. Okay, let's do a quick one. Let's do one more quick one. Where's my Excel table? Where's my Excel table? Okay, maybe let's do, wait. Let's do another common section size that I used last time. 254,146, yeah, 254,146, 37. Yeah, okay. How do I share? Okay, share, continue. Share this screen. Okay, all right. Okay, let's do one more example. Okay. So I want you to classify 254,146 UB 37 grade S275. Okay. So get me the, can you go to the Excel now? Get me all the dimensions of this section. What is the age? What is the width? What is TF? What is no. This is TW. What is TW? What is TF? And what is the root radius? R. Okay. Open up the Excel. Give me all the sizes.
The H,
Mm. Yep.
256.
Ngam.
Yeah, 256.
All right. Okay. The B.
146.4.
146.4. Okay.
6.3 for TW.
6.3.
Yeah.
Okay.
And TF 10.9.
10.9. Okay.
R 7.6.
R 7.6. Okay. Good. Thank you. Okay. So let's find the ratio first. Okay. We find the ratio first. Okay. So for web, C over TW. Now, obviously, C for the web is measured from the root radius to the root radius. Okay, it's that one there. That's a C. So the C is, let me just do the calculation for you. Okay, so 256 minus the TF at the top and TF at the bottom. 2TF lah. 2TF minus 2TF. And then minus 2R, 2 root radius. Okay. So 256 minus 2TF. 10.9 minus 10.9. Minus 2 root radius. 7.6 minus 7.6. 219. Okay, help me double check if I'm wrong. But I think it's 219. So therefore, the radius for the ratio for web is 219 mm divided by TW 6.3 mm. 219 divided by 6.3. 34.76. 34.76. Yeah, no unit, no unit. 34.76. Okay. Now for the flange, same. C divided by BF. Okay. So let's the C for the flange is this, measured from the end of the root radius. So the C for the flange is the total flange width, which is B, minus TW, the web thickness, minus 2 times the radius, the whole thing divided by 2. Okay? So the C for the flange is the total flange width, 146.4, divided by the web of the web thickness, 6.3, minus 2 times the root radius, the whole thing divided by 2 to get just the C on one side, because otherwise this C is for both sides. Yeah. Okay, so 146.4 divided by 6.3 minus 7.62 times divided by 2. 62.46. 62.45. Everyone check my calculation, make sure I didn't make any mistake. Therefore, so 62.45. 45 divided by TF. TF is 10.9. Divide by 10.9. 5.73. Okay, 5.73. Agree?
Yes, I agree, doctor.
Agree. Okay. Okay, now, so these are the ratio. Now we want to find the limits. Now we want to find the limits. So again, to find the limit, we need to know the epsilon first. The epsilon, now I'm using grade 275. Grade 275, if you look at the table, the epsilon is also 0.92. Okay? For grade 275, the epsilon is 0.92. It's in my notes. Those two tables right at the bottom. Yeah, it tells you 275, epsilon is 0.92. Okay, now web. Let's for class 1. Okay. So limits. For class 1, the web C over TW has to be, should be the same for this one. 72. Okay, has to be 72 epsilon, which is 72 times 0.92. Actually, the limits are the same, 66.24. Okay, now, so for the web, the limit for class 1 is 66.24. Sorry. Less than has to be less than or equals to, less than or equals to, less than equals to. Okay, so for class 1, the C over TW has to be less than or equals to 72 epsilon, which is 66.24. Now, our web ratio is how much? Only 34. 34.76. 34.76 is less than 666.24. Therefore, web is class 1. Okay, now for flange, to qualify class 1, the C over TF has to be less than or equals to 9 epsilon. 9 epsilon is 9 times 0 0.92, 8.28. I always make this mistake. It's not equals. It's less than equals to, less than equals to. Okay, so for class 1, for the flange, the C over TF has to be less than or equals to 9 epsilon, which is 8.28. Now, our actual ratio is what? 5.73 only. So it is less than 8.28. Therefore, also class 1. Therefore, the section is class 1. Because the flange and webs are class 1. Okay, is that clear?
Yes, clear.
Yeah, Doctor.
Yeah. Okay. So I think that is pretty self-explanatory. I don't think you need more examples, right? You can practice on your own. Just simply you can simply so you can simply go through this Excel table. You simply choose whichever section you want and you do the check. Yeah, you can just play around. Simply choose any section you want and then you can do the check yourself. Okay. So this table is actually from the internet. Okay. There's a website where you can get all this data, and then it allows you to download an Excel version of this. Now, the version that I downloaded, I actually did some edit. Actually, in the full Excel table, it already tells you whether the section is class 1 or class 2 or class 3 or class 4. Okay, it actually tells you that, but I removed it I removed it from this table because I want you to check it for yourself. But in real life, they actually check it for you already. Yeah, but you still need to know how to check it. That's why I removed that section. There's actually a column that tells you whether this section is class 1 or class 2 or class 3 or class 4. Okay, but I removed it from this Excel. Okay. Okay, so you get familiar with this Excel table. You get familiar on how to check the classification. All right, and then you do the revision. Anything you are not clear, you can ask me next week during class. All right. Give me a second. Wait for me while I prepare the attendance. All right. Attendance.